Okay, welcome back, guys. I just wanted to talk about question 20 because I noticed a few of you have an issue with it. So I wanted to talk about it for the benefit of everybody. So here we're given two particles, and these particles are undergoing motion. The motion concerned here is two-dimensional. And as you might recall from my presentation in class, the motions in the two different directions are independent of one another. The only thing that relates them is that time ticks at the same rate for both. So what that means is we can isolate the different quantities according to their dimensions, that is, according to their x and y directions. For instance, particle A, initially when we begin to trace this motion, passes, its x-coordinate is 0 meters. That's when we begin to take note of this motion, and its initial y position is 30 meters. That's what we're told over here. That's what its initial y coordinate is, and it's moving at 3 meters per second along the x direction and not advancing along the y direction. And because it's moving at a constant velocity, we conclude that the x and y components of its accelerations are 0. This is what I've done to try to capture all the details in a nice concrete way where I could keep track of what I have and what I don't have. If I perform the same analysis for particle B, this is what I have. Over here, particle B begins at the origin of our coordinate system, so its x and y components are 0, x and y coordinates are 0. And because it begins from a rest, we conclude that the velocity components are both 0. What is different is that its acceleration is constant with a magnitude of 0.4 meters per second squared. But because this acceleration is at an angle, we need to resolve it into its x component and y component. And I have done so over here, and these are the respective components. And I've kept the expressions as general as possible in order to demonstrate how to approach these questions with as much generality as possible. Of course, we will specialize things to this specific problems as needed, but right now, let's keep things general. Okay, the intention here is to find the angle theta at which we must launch particle B in order to orchestrate a collision. This is what we're trying to figure out. We're trying to find out what's the appropriate angle at which we ought to launch particle B with these conditions so that it will collide with particle A, which is undergoing motion as captured by those conditions. Consider what collision means. Collision means the positions of the two particles have to be the same. So the x-coordinate of A must be the same as that of B, and the y-coordinate of A must also be the same as that of B at the same time. This is quite important. Sameness in position at different times does not mean collision, but sameness of position at the same time means you will end up with a collision. Of course, with these conditions, we know that this problem at hand will primarily be focused on the position quantity. So we know that any object undergoing constant acceleration will obey the equations of motion, and the general expression of which is boxed over here. Now we need to specialize this equation for both particle A in the x direction and particle B in the x direction. If we do so, we end up with this for particle A and with that for particle B. These expressions are simply obtained by substituting these values in that equation. You could try it out on your own. And the same could be done on the y direction. In the y direction, the position function is given by that. And when we specialize for particle A, we obtain that, and for particle B, we obtain that. Now it's time to impose our constraints. Constraint number 1 means this function is going to equal this function. And what do we learn from that? We learn that the time at which this will be true, that is where the x coordinates are going to coincide, the time is given by that. T is going to be 6 over acceleration times sine theta. And I've given that a name, that equation, name alpha. Now let's again impose constraint number 2, because remember, sameness in position, both x and y. Sameness in position in the y direction is equivalent to equating these two, and what we learn from that is contained in equation beta. Again, we want these two conditions to be true at the same time. Well, we know at what time this sameness of the x positions is. It's at that time. So now let's substitute this t for the y for constraint number 2. Substitute the time here into constraint number 2. Basically, substitute alpha into beta. What you're going to end up with is something that looks like this. And when you cross multiply and you clean up this equation, it's going to look something like that. The sine theta squared can be rewritten as 1 minus cosine squared of theta. And again, when you clean that up, you're going to end up with something that looks like this. So you are almost there in obtaining the necessary angle, or the angle necessary to induce a collision. In order to make things clear for you, I commend you substitute for cosine, substitute q. Every time you see a cosine, replace that with a q, and then this equation, you will notice, is nothing more than a quadratic equation. And basically this is equivalent to finding the roots of the quadratic equation. And once you found the roots, basically find the q's. Then you can replace q back with cosine of theta, and then effectively find theta. I hope that gives you a bit of a roadmap as to how to take care of this. Should you have any more problems, feel free to let me know. Thank you.